Okay, Sumegha, you all ready?
Yeah. Can you see my slides?
Yeah, we see your slides.
Okay. Can you see them moving too?
And EPFL, are you guys set? Do you have everything's working for you? I'm going to take
I see many of them standing.
Okay, let's hope that EPFL is going to complain if something is wrong. Okay, we're delighted to have Sumegha Garg, who is a postdoc at Harvard, to continue a theme which we also heard about from Greg Valiant a few days ago on memory sample trade-offs in learning. So Sumegha, go ahead.
Okay. Yeah, thanks, Sam, for introduction. Today, I'll be talking about an extractor-based approach to proving memory sample trade-offs. This talk is based on joint work with Pravesh, Ran, and Avishai. I am excited to be presenting in this workshop, and I want to at least get one of you excited to work in the field. So please ask me questions. Okay, so in this talk, the computation resource that we would care about is memory. And we would ask the question that if learning is infeasible under memory constraints, the type of problems that we will study is such that statistically, with the small number of samples, we can solve the learning problem, but under low memory constraints, we would not be able to solve the problem even with exponential number of samples. So with increasing scale of learning problems and limited memory on devices, it is not only philosophically important, but also becoming practically important to study the feasibility of learning under memory constraints. And secondly, many learning algorithms try to learn a concept or hypothesis class by modeling it as a neural network. Such an algorithm keeps in memory some neural network and updates the weights when new samples arrive. And memory used by such an algorithm is the size of the network, which corresponds to a low memory algorithm if the network size is small. And this is just to motivate the fact that we are trying to use low memory algorithms in practice. And it is important to study what kind of hypothesis classes these low memory algorithms can learn. Okay, so a brief description of the learner problem that a brief description of the learning model that we will look at in this talk is of the following form. A learner tries to learn a function f, where you have the promise that this function f belongs to this hypothesis class capital H, and it tries to learn this from a sequence of samples of the form a comma f of a. That is, you get a sample from the set capital A, and then the evaluation of f at this sample, and you keep on getting these sequence of evaluations one by one, and you want to figure out what the hidden function f is. Some of you might know the setting as the setting of online learning, and in this talk we will also have a distribution over the capital set A from which these sample points are being generated. Shamir in 2014 and Steinert, Violet, Weger in 2015 asked this question, that can one prove unconditionally stronger lower bounds on the number of samples needed for learning under memory constraints in the streaming model, that is when samples are viewed one by one. And in this talk, we will do a brief survey of the results that results that were proven in this area after this question was asked. So in the first section, I will give you the first example of a memory sample trade-off that was proven in 2016 for a problem called parity learning. Then I will just summarize the results that were proven after the first result. Then I will talk about a joint work with Ran and Avishai, where we gave an extractor-based approach to proving memory sample trade-offs for a large class of learning problems. then we will see a bit of the proof techniques that are used in proving these lower bounds. And finally, to do justice to this workshop, I want to give you the implications of these results for proving hardness of refutation of CSPs under low memory. And this is joint work with Pravesh and Ram. Okay, so let's look at the parity learning problem. Under the parity learning problem, an unknown function f is represented by an n-bit string, and it is chosen uniformly at random from the set of n-bit strings. And a learner tries to learn f from a sequence of samples of the form a, b, where a is another uniformly randomly chosen n-bit string, and b is the inner product of a with the unknown function f in field 2. That is, b is some I ai times fi mod 2. So in other words, what is hidden from the learner are n variables, and learner is getting random binary linear equations in those variables one by one, and it needs to solve for the hidden n variables. And the claim of and the theorem is that this problem is hard to learn with low memory, where we will quantify the memory requirement after a few slides. So I want to do an exercise to intuitively understand why this problem is hard to learn in low memory. I will give you a sequence of equations in 5 variables, and please try to solve for them with your brain's memory, but do not jot down the equations on your notebook. Okay, any guesses?
1, 0. I don't know. I think the first is 1 and the third is 0.
I'm not sure she hears you unless we use the mic. Ryan says that there's some ones and some zeros.
Yeah.
That's true. Okay, so I predict you wouldn't have been able to solve it unless you have a very good memory. So the answer is 0, 1, 1, 0, 1. So I intentionally gave you many more than 5 equations. It would have been easy to figure out what is the solution by just writing down 5 equations and doing Gaussian elimination to figure out the hidden variables. So this corresponds to a parity learner that uses order n samples and order n square memory. So you just store the first order n samples, and with high probability, these would be linearly independent, and you can use Gaussian elimination to solve the linear equations. And maybe another thing you might have tried is I am going to just guess what the function f is and try to see if that fits the equations. And then a solid learner would be, it tries out all possibilities of f one by one and tries for the next order n samples if this f fits the criteria. So this requires only order n memory to store the current guess for f, but it requires exponential number of samples to learn. And it is natural to ask, can you get something in the middle that maybe you store some samples, do some computations, and then you do not need to, you reduce some possibilities of f, and you do not need to go through exponential number of samples, but you also not order n square memory. So, but this is not the case. In a breakthrough result in 2016, Rand proved that any algorithm for parity learning of size n requires either memory of n squared by 25 bits or exponential number of samples to learn. And this trade-off between the memory required by the learner and the samples required by the learner gives this field the name of memory sample trade-off. So the main motivation to study these memory sample lower bounds obviously comes from learning theory. And then the second fascinating application of these lower bounds is in the area of bounded storage cryptography, where we try to construct cryptographic protocols that are secure against bounded memory adversaries. And there has been a good line of work trying to construct these cryptographic protocols using memory sample lower bounds. So to give a teaser, the lower bound of run in 2016 for Parity Learned gives us a cryptographic scheme to exchange messages between two players, where the secret key shared by them is just n bits long. An encryption and decryption of each message bit takes n units of time, but these players can exchange exponential number of messages amongst them, and those messages would be unconditionally secure as long as the attacker's memory size is less than n squared by 25 bits. And then the last motivation obviously comes from complexity theory, where time-space lower bounds have been studied in many models, and the streaming model that we study helps us prove very strong lower bounds, unconditional lower bounds. Okay. Any questions till now? Okay, good. So, subsequently, a paper in 2017 generalized these memory sample trade-offs to learning sparse parities, where the hidden function has only a few ones. And then there has been a lot of work to generalize these memory sample trade-offs to even larger class of learning problems. Today, I will focus on a joint work with Rana and Avishai, where we gave an extractor-based approach to proving such memory sample trade-offs for a large class of learning problems. So this result implied all the previous results. That is, we even generalized the technique, and it gave some new lower bounds. And I want to mention that this proof technique closely follows the proof technique of a sequel to the first paper of Ran in 2017. And I will not go into the details of this independent work, but in 2018, Beam, Ovis, and Yang independently proved some related lower bounds. Okay. You might remember this generalization from Greg's talk on Monday. So in a beautiful work, Vatsal, Aaron, and Greg generalized these memory sample trade-offs to a problem in continuous optimization, where they prove that any algorithm performing linear regression over a stream of d-dimensional examples either use quadratic memory or have a slower rate of convergence than which can be achieved without the memory constraint. So this provably tells us that first order methods that use low memory have slower rate of convergence. Okay, and then there has been a lot of related work in the area, for example, generalizing these trade-offs to learning under multiple passes over the stream, proving memory sample trade-offs for distinguishing or testing problems, or even characterizing memory bounded learning, or proving such trade-offs for quantum memory bounded algorithms. So this is all I want to say about the related work. If you want to know more or want some references, please contact me. Okay. So now let's go into more technical details of this paper, where we study an extractor-based approach to lower bounds. So we formulate the learning problem as a matrix, as done by previous papers. let capital A and capital F be two finite sets, and matrix M be plus minus one matrix where the rows are indexed by elements in the set capital A and columns are indexed by the elements in the set capital F. Think of the set capital F as the concept class and the set capital A as the possible samples. So this is the matrix, and then the learning problem that we defined they're defined with respect to this matrix M is as follows. So a function F is chosen from the set capital F, that is a uniformly random column is chosen to be the unknown function F. And then a learner tries to learn F from a stream of samples of the form A, B, where in each sample a random row is chosen. And then what you are given is that the matrix entry at this row and the unknown function F. So you keep on getting row indexes and the entry at that index for that unknown function F, and then you want to from this kind of information you want to figure out which column is used to generate these sequence of samples. This is the learning problem corresponding to a matrix, and we want to study what properties of this matrix makes it an easy or a hard problem to learn with low memory algorithms. So this is the property that we study in this paper. Let's see, matrix M has the following property, that any submatrix of M which has at least 2 to the minus k fraction of rows and 2 to the minus L fraction of columns, it has bias of at most 2 to the minus R. That is, if you average out the entries in this submatrix, which are plus minus 1, then that average, then the absolute value of that average is at most 2 to the minus R. So intuitively, this is saying that most large submatrices are unbiased. And if matrix M has this property, then we can prove that any learning algorithm for this learning, for the learning problem corresponding to this matrix requires either KL memory or exponential in R number of samples. So this, we say that this is an extractor-based property because this condition basically corresponds to the fact that this matrix M is a two-source extractor. But that is not important for the talk. It's just this fact is needed. Okay. Any questions? So this is the lower bound that we prove. The applications of this lower bound is that we can prove that low degree polynomials are hard to learn under low memory, so which corresponds to the following problem. Let's say a learner tries to learn an n-variate multilinear polynomial P, which has degree at most D, from random evaluations of P over F to the n. That is, a polynomial of degree D is hidden, and at every step you're getting a sample point and the evaluation of P at that sample point. And then you want to learn what the hidden polynomial P is. So statistically, you can just store the first n to the D points and evaluations of the polynomial P on those points, and you can solve for the hidden polynomial P. And we prove, and this corresponds to a n to the D plus 1 memory algorithm. And we are able to prove that this is tight. That is, you either require a memory of n to the D plus 1 or exponential number of samples. And then we are also able to prove that learning from sparse equations is hard. That is, a learner tries to learn F, which is, think of F as n variables, from random sparse linear equations of sparse TL. That is, n variables are hidden, and at every step you get an equation which depends only on L variables, and you want to learn the hidden satisfying assignment or the hidden X. And for this, we can show that either you either require NL memory or exponential L number of samples. And this is a result that we will use in proving sample lower bounds for refuting CSPs in the streaming model under memory constraints, which I will talk about after the proof overview. But any questions till now? So to prove our lower bound, we model the learning algorithm as a branching program as done by previous papers. A learning algorithm that uses S bits of memory and M samples can be modeled as a branching program of length M and width 2 to the S. A branching program basically is an acyclic directed graph where the vertices are divided into M layers, and each layer has D vertices in them. Each vertex in a layer represents a memory state of the learning algorithm. So that means that D is equal to 2 to the memory. And edges are present only from a layer to the next layer, and it represents the memory state change after seeing the ith sample. So each non-leaf vertex has 2 to the n prime plus 1 outgoing edges, one for each possible sample of the form A comma B. So let's say this is the ith layer, and there is an edge labeled A comma B going from this vertex to this vertex. So this means that if my learning algorithm was in this memory state and it read A comma B as the next sample, then it will go to this memory state. A comma B as the ith sample, then it will go to this memory state. So the samples A1, B1, a sequence of samples A1, B1, A2, B2, and AM, BM corresponds to a computation path in this branching program. So basically, you can traverse what memory states a learning algorithm is in while doing the computation on this sequence of samples by going through the branching program one by one, layer by layer, and you start at the start vertex. You look at the first sample, go to this memory state, and so on, and then you reach in a memory. You reach at a vertex in the last layer. And all vertices in the last layer are labeled by a guess for the unknown function f, that is f hat v, which is the output of the algorithm if the computation path reached this memory state. So the success probability of a learning algorithm can be modeled as the probability that f hat v is equal to f, which was used to generate these samples. Any questions for the branching program model? Okay. So this means that for every vertex P, we can. It is good to analyze the progress of these belief distributions, that is PF given V, which corresponds to the distribution of the function f conditioned on the event that the computation path reaches V. So this is like the best knowledge that you can have about the unknown function f, conditioned on the fact that it reached this memory state after I steps. And we call a vertex significant if we call a vertex significant if the L2 norm of this belief distribution is large. You do not need to understand this mathematical formulation, but intuitively this is saying that this vertex V already has some amount of information about the unknown function f. So if okay, then let's say PRV is the probability that the path reaches this vertex V. And we want to show that if V is a significant vertex, then the probability of reaching this vertex is exponentially small in K times L. That is, if and then if there are less than 2 to the order KL vertices in the branching program, which is the case if the memory of the learning algorithm was less than KL, then with high probability, we reach a non-significant vertex. A non-significant vertex is such that the L2 norm is small. That is, there are many possibilities of F such that we would reach the same vertex V. So we cannot be, we should not be able to guess the correct F with high probability. So this proof outline is saying we prove that either we reach a non-significant, so we reach a non-significant with high probability, and those vertices do not tell us enough about F. Okay, so this is the main hardness. This is where this is the main technical part of the proof. To give you more technical details on how to prove such a statement, we analyze a progress function as done by the previous paper of Ran in 2017. So for every layer Li and every significant vertex S, we define a progress function that basically measures how close this layer is from how close is this layer to the significant vertex S. So it's averaging over the vertices in the layer, in the ith layer, and this is basically inner product of the belief distributions, and it's measuring how close is this vertex V in layer I to the vertex S. In the start Z0, that is the start vertex, this function has very small value, because in the start you are at the belief distribution condition on the start vertex is uniform distribution over all the function set, and it is not at all close to reaching the significant vertex S. And then we show that using the extractor-based property that Zi should be growing very slowly. That is Z0 is basically very close to Zm. But let's say the significant vertex belongs to the last layer. Then Zm can be small only if the probability of reaching the significant vertex is small. And this allows us to prove that if S is significant, then probability of S is less than equal to, is exponentially small in K times L. Okay, any questions? Good. Okay, if I lost you in the middle, this is the time to tune back in. Now we will shift focus and talk about the implications for of these results for proving hardness of refuting CSPs by low memory algorithms. This is joint work with Pravesh and Ran. And so in this work, we study a related problem, a problem related to the problem of refuting CSPs under the streaming model. This problem is as follows. Let's fix a predicate P, which takes in K bits and outputs a single bit. And the goal here is that you have a bounded memory algorithm, and which wants to distinguish between these two distributions. That is, in the first setting, you're getting these constraint satisfaction problems with predicate P on n variables, where the constraints are randomly generated. And in the second setting, you are getting constraints such that there exists a satisfying assignment for all the constraints. And it is in the streaming model, that is, constraints are arriving one by one in a stream. So if the number of when the number of constraints are much larger than n, then we know that CSPs with balanced predicates P become with random CSPs with balanced predicate P become unsatisfiable with high probability. So this means that for in that regime, when constraints are much greater than the number of variables n, in that setting, a refutation algorithm, that is an algorithm that that refutes that is able to refute that that a constraint satisfaction problem is unsatisfiable, is satisfiable, is able to distinguish between these two distributions, because in this distribution the refutation algorithm will always output 0 and it would output 1 in this distribution, in the first distribution where the constraints are randomly generated. So this means that in the regime where constraints are much greater than n, refutation is at least as hard as distinguishing between random CSPs and satisfiable ones. So whatever bounds we get for distinguishing between these two distributions in that regime, though those bounds also hold for refutation algorithms. Any questions? Okay, so more formally, our problem setup is as follows. You have an X, which is an n-bit string, and it is chosen uniformly at random. Then at each step I, Si is another randomly chosen subset of size k. Think of Si is a subset of n, and Si would be used to dictate the ith constraint in. Okay, so at each step I, Si is a randomly chosen subset of size k. Si would be used to generate the ith constraint, and Si basically dictates the k variables that the ith constraint would be on. So the distinguisher either sees a stream of samples of the form Si comma P of x Si, or it sees a stream of samples of the form Si comma Bi, where Bi is chosen uniformly at random. Here x Si is just the projection of x to coordinates of Si. So this can be thought of as a constraint, because Si is the k variables that the constraint P is on, and then in this stream of constraints, which corresponds to a CSP, all the constraints are satisfied by this unknown hidden n-bit string x, whereas in the other distribution, these are randomly generated constraints, and the learner needs to distinguish between these two streams. Okay. So we prove that, as mentioned before, using the result that learning from sparse equations is hard for low memory algorithms, we can prove that any algorithm that distinguishes random k XOR CSPs on n variables from k XOR CSPs with a satisfying assignment under the streaming model requires either nk memory or exponential in k constraints. So for k much greater than log n, it says that if refuting CSPs, which depend on refuting CSPs with XOR predicate, which depend on much greater than log n variables, is hard for algorithms that are using even superlinear memory when the number of constraints is less than exponential in k. Any questions?
So sorry, I'm a little confused. So often these memory sample lower bounds have the flavor of saying that some natural algorithm is optimal. Like if you go a little bit below the memory used by some natural algorithm, then you'll require exponential samples. Maybe I just got lost for a second, but is there a natural algorithm to think about here?
Yeah, so okay, so for the question of learning from sparse equations, the natural algorithm uses n times k times log n memory. Basically, each sample requires k log n memory to store for storage, and you can store n samples.
Okay, and once you have n samples, then it becomes easy.
Yeah, so it's information theoretically easy.
Yeah. Okay,
Yeah.
Thanks.
Okay, great. So now you will ask that what about, but mostly we care about, let's say, 3-sat CSPs with 3-sat or so on. So what about refutation? Can we prove that refutation is hard for algorithms that use low memory when k is much less than log n? So we do get some hardness results in that case, but only for algorithms that use sublinear memory. So here by sublinear memory, I mean that sublinear in the number of variables, that is n. So, so when we are talking about algorithms that use sublinear memory, we do not need to use the machinery from the previous, the heavy machinery to prove our lower bounds from the previous papers. This is because it is very easy to show that because it is sublinear memory, then even in the satisfiable case, most vertices would not have enough information about which X was used to generate these constraints. And this is like a very easy argument. So for sublinear memory algorithms, we are able to prove stronger lower bounds on the number of constraints needed to refute. And we can generalize these trade-offs even for CSPs with T-resilient predicates and not just the XOR predicate. So T-resiliency resiliency of a predicate P was shown to be necessary for proving hardness of refutation of CSPs in a different computational model in previous papers. And it's interesting that this also shows up in our lower bounds. So very briefly, a predicate P is a T-resilient predicate if P has zero correlation with every parity function on at most T-1 bits. So XOR function is K-resilient, and then there are many functions that are T-resilient, and we get lower bounds that depend on this parameter T. So formally, we are able to prove that any algorithms that distinguish random CSPs with a T-resilient predicate P on n variables from satisfiable ones when the constraints are arriving in a streaming fashion require either a memory of size n to the epsilon or n to the t times 1 minus epsilon constraints. This trade-off holds for many values for all values of epsilon, and this is basically showing that refutation, because this is whenever this is greater than n, much greater than n, it is showing that refutation is hard algorithms that are using n to the epsilon bits of memory. Okay, yeah, that's it. Thanks.
Thanks, Sumegha. We have time for a couple questions from here or Zoom or EPFL. How about on the EPFL side? Well, one question is what are you, in your view, what are some exciting future directions for this line of work?
So, okay, so the future, okay, so one is that we want to go beyond the extractor-based technique to prove such lower bounds. So the extractor-based property is a very strong property. It's saying that even if you choose, even if you have n bits of information about, even if you have like n by 2 bits of information about the function, and let's say n by 2 bits of information about the sample, then also you cannot figure out what the next what the matrix entry can be. And this is a very strong property, and we want to go beyond this and develop techniques to prove memory sample lower bounds for even larger class of learning problems. So one problem that to look at is noisy parity. So in noisy parity, when each bit is correct only with probability half plus epsilon, for that, okay, let me tell you the problem. So under noisy parity, again, it's the same thing. A parity is hidden, and then at each time step, you are getting an equation, but the bit that you get with that equation is correct only with probability half plus epsilon. And you can store n by epsilon square samples, and this gives you an n square by epsilon square memory lower bound, upper bound to solve this problem. Whereas the best lower bound that we know using the extractor-based techniques is that you require either n square by epsilon memory or exponential number of samples. And I believe it's a very exciting problem to work on to get a tighter lower bound for noisy parity.
Yeah, we have another. Let me run the mic over.
Let's see. So, and notice this lower bound is n over t to the omega t times one minus epsilon. I guess what is known, say, specifically for 3 XOR?
Yeah, for 3 XOR, it's nothing.
And Sumegha, what do you expect the result to be for example, 3 XOR?
So, okay, so I believe that 3 XOR, we shouldn't be able, these techniques wouldn't help us in the setting of 3 XOR, but very briefly, I thought about using, so there are these results where you prove that solving max cut is finding a true approximation to max cut in a streaming setting is hard for algorithms that use n bits of space. And maybe those kind of techniques would be helpful in proving these proving results for 3 XOR.
And what would the lower bounds be? Like, what do you expect the trade-off between memory and constraints? Like, what would match an upper bound?
I assume so. I don't know. I would guess that it might match. Like I cannot on the top of my head think of a better low memory algorithm.
Okay, thanks.
Yeah, thanks.
Okay, thanks Sumegha once more.
Okay, yeah, thanks.
And we're really doing a good job with the schedule today. I'm so proud of us.